Okay, let's dive in. Our source today, well, it takes us on this incredible journey, doesn't it? 15 billion years. And our guide, none other than the master himself, Carl Sagan.
Absolutely. We're talking Cosmos. It's really more than just a book. It's his whole vision laid out.
It really is. He takes the entire history of the universe,
Yeah. Yeah.
matter, life, consciousness, and just weaves it into this epic story, a story about us, about civilization's rise, which was, as he points out, pretty fragile.
That's the key. So our mission here really is to kind of give you a shortcut to grasping that huge perspective. We're talking cosmic evolution, the sometimes heartbreaking story of knowledge itself, and those big scientific shifts that just changed how we see everything.
Totally changed the game.
And you feel it right from the start, that dedication for Andrian. It's so personal, yet set against this backdrop of, well, everything. In the vastness of space and the immensity of time, he connects love and the universe right there. It's beautiful.
It really is. And then boom, that opening line hits you. The cosmos is all that is or ever was or ever will be. You get that tingle, right? That feeling of looking into something immense, almost dizzying.
A sense of vertigo, yeah. Because you know you're touching on the biggest mysteries there are.
But here's the thing Sagan does so brilliantly.
Right.
He doesn't leave it as just some abstract wonder. He ties that cosmic feeling, that awe, directly to our survival.
Exactly. He says we're basically lost, right, between immensity and eternity on this tiny planetary home. And yet, knowing the cosmos, understanding our place in it, that's the key. It's not optional. It's what we need to survive.
Our future depends on it. It makes science feel vital, not just academic. And he gives us the tools we need for this kind of deep dive right up front. Imagination and skepticism.
The twin engines, really. You need that imagination to even conceive of other worlds, of possibilities beyond what we see, to go to places that never were, as he puts it. Without that, you're stuck.
But you can't just dream. You need the other side, the skepticism. That's the rigorous part, the testing, the reality check is how you tell the difference between a cool idea and actual fact.
Fancy versus fact.
Yeah.
Because the cosmos is incredibly rich, full of these amazing connections, this subtle machinery. You need both imagination to see the possibilities and skepticism to nail down what's real.
Okay, so let's use those tools right now. Let's establish that cosmic perspective. Because honestly, without it, nothing else really makes sense, does it?
Not on this scale, no. And the first thing to go, our ego, our sense of being important, Sagan is pretty blunt about where we actually are.
It really is. Our galactic neighborhood, the local group, he calls it sparse and obscure and unpretentious. We're not exactly downtown, cosmically speaking.
Not even close. And even our own galaxy, the Milky Way. I mean, 400 billion stars, that's a staggering number, but where's our sun? Tucked away in an obscure locale near the edge of a distant spiral arm. We're out in the suburbs, maybe even further out.
The numbers themselves are just,
Yeah.
they're possible to really visualize. So we have to focus on the contrast, the diversity. Think about the stars themselves. You've got these massive, flimsy ones like soap bubbles, he says, big enough to swallow 10,000 suns.
Those are the young ones, the blue giants. Burning bright, burning fast, living life in the fast lane cosmically.
And then the other end of the spectrum, these incredibly dense, dying stars, neutron stars, right? The size of a town, but 100 trillion times denser than lead.
A teaspoonful would weigh more than a mountain. It's unbelievable. That's what happens when gravity just crushes everything down. The end state for some stars.
And we can actually see this life cycle play out in their colors. It's like a visual story. Blue means hot and young. Yellow, like our sun, is kind of middle-aged, stable.
Then they swell up into these huge, cooler red giants that's old age setting in. And finally, they collapse down into those tiny, faint white dwarfs, or even black dwarfs, the last embers. And this whole city of 400 billion stars, the Milky Way, it's all moving together, circling some distant center we can barely even see.
Okay, this is where it gets really wild. Connecting space and time. The speed of light. It's fast, obviously, but it's not infinite.
And that finite speed changes everything about how we see the universe. Because light takes time to travel. Looking out into space is looking back into time. You can't separate them. to
So give us an example, like Beta Andromedae, a relatively close star.
Right, only about 75 light years away, which sounds far, but cosmically it's next door. The light we see from it tonight actually left that star 75 years ago, around 1950, let's say.
So we're seeing it as it was when Einstein was publishing his special theory of relativity on Earth. That's mind-bending.
It is. Now, stretch that out. Look at the Andromeda Galaxy, M31, our nearest big galactic neighbor.
How far is that one?
2 million light years. So the light from Andromeda hitting your telescope tonight started its journey 2 million years ago. Before Homo sapiens even walked the Earth, we're looking at pre-human history.
Wow. Okay. And the furthest things, quasars.
Quasars, yeah. Some are 8, maybe 10 billion light years away. We're seeing them as they were before our own Milky Way galaxy had even fully formed. Before the Earth itself existed, the universe is like this giant time machine.
Ancient history playing out right before our eyes. Okay, let's zoom back in a bit. From the edge of the observable universe to our own solar system's edge. The cometary cloud.
The Oort cloud, this vast spherical swarm of icy bodies way, way out there, maybe a trillion of them. Giant snowballs. Really ice, rock, and importantly, organic molecules, leftovers from when the solar system formed.
How big are these things typically?
The nucleus itself, pretty small, maybe a kilometer across, give or take. Most just drift out there in the cold dark. But sometimes, a passing star's gravity gives one a nudge.
And down it falls, towards the sun.
Exactly. And as it gets closer, the sun's heat starts to work on it. The ice doesn't melt. It sublimates, turns straight into gas, carrying dust with it. And that's what creates the spectacular tail.
It's amazing, isn't it? That tiny, dirty snowball, maybe a kilometer wide, produces this tail that can stretch for millions of kilometers. As great as the distances between the worlds, Sagan says, you can see why ancient people were both terrified and awestruck.
Absolutely. They didn't have the science to explain it, just this incredible apparition in the sky.
And seeing that vastness, that immense cosmic stage, it really underscores how precious and, well, precarious the rise of human knowledge actually was. It all arguably started in one place, one time, the Ionian Awakening.
Around 600 to 400 BC, this explosion of thought in the Eastern Mediterranean. And it wasn't an accident of geography, was it?
No, it seems like it was the result of mixing. You had African, Asian, European cultures all meeting, trading ideas, challenging each other.
Right.
It wasn't isolated. Power was often with merchants, people who valued, practical things, technology, new ideas, not rigid dogma.
That melting pot fostered what Sagan calls the great idea, the truly radical notion that maybe, just maybe, you could understand the world without needing gods to explain everything, using principles, natural laws, cause and effect.
Instead of just saying Poseidon was angry for every storm.
Exactly. It was a fundamental shift in thinking. Look at the pioneers. Thales, he predicted an eclipse. That showed nature wasn't just random whims, it followed patterns. And he used simple geometry, shadows to measure a pyramid's height. Practical genius.
Then Anaximander took it even further. The Earth just floats, unsupported. That was radical. And his idea about life originating from simpler forms, maybe from fish. Yeah. It's like a proto-evolution, millennia early.
Incredible foresight. And then Democritus, he basically invents materialism. He comes up with the atom, the uncuttable particle. Everything he said is just atoms moving in the void.
Nothing exists but atoms in the void. That's such a stark, purely scientific statement. He even thought other worlds just formed and decayed naturally. No need for a creator. It really laid the groundwork for physics.
That whole Ionian way of thinking, that rational inquiry, it reached its peak, didn't it, a couple of centuries later, at the Library of Alexandria.
Oh, the library. What a place that must have been. 3rd century BC, the absolute center of knowledge for the ancient world.
Imagine the scale. 500,000 scrolls, all handwritten papyrus. They had agents out buying whole libraries. They even, reportedly, had police search ships in the harbor for books to copy. Talk about a thirst for knowledge.
An intellectual monopoly, really. But the tragedy is how much we lost when it declined.
It's staggering. Think about Aristarchus. He figured out the Earth orbits the sun, and that the stars must be incredibly far away to explain why they don't seem to shift, the correct model.
And it was just lost for almost 2,000 years.
Lost, overwritten by the Earth-centered model of Ptolemy, which became dogma after the library's influence faded. We basically took a massive detour.
And historical records, too, like that historian Berossus, claiming history went back hundreds of thousands of years before a great flood.
Yeah, 432,000 years from creation to flood, he apparently wrote. That implies a sense of deep time, completely at odds with the much shorter chronologies that later became dominant in the West. We lost that perspective.
So the library's decline, its eventual destruction. It wasn't just losing books, it was losing a whole way of thinking, losing continuity with that earlier, bolder scientific age. And Hypatia's story really brings that home.
Hypatia is such a tragic figure, born around 370 AD, a brilliant woman, mathematician, astronomer, philosopher, right when that classical world was crumbling.
And science, reason, independent, thought it was becoming associated with paganism, right, as the church was consolidating power.
Exactly. It was a dangerous time to be a public intellectual outside the approved framework, and the end for her was just horrific. A mob driven by fanaticism dragged her into a church in 415 AD.
And they didn't just kill her.
No, they flayed her. With oyster shells, or abalone shells, the stories say. It's barbaric. Her murder symbolizes the death of that classical tradition of inquiry, the lights going out across the ancient world.
And the scale of the loss. You mentioned Sophocles. How many of his plays survived compared to what the library supposedly held?
They knew of 123 plays by Sophocles in Alexandria. We have 7. Just 7 survived the centuries of neglect, destruction, and, frankly, deliberate suppression. It's a chilling reminder of how easily knowledge can vanish.
It really is, how fragile it all is.
And it took a long, long time for that scientific spirit, that reliance on evidence, to really reemerge. Johannes Kepler is a perfect example of that struggle, the internal battle between wanting something to be true and facing the actual facts.
Kepler started out very mystical, didn't he? His first big idea, the cosmic mystery, was all about beauty and harmony.
Pure imagination. He was convinced the orbits of the planets had to be structured around the 5 perfect Platonic solids, the cube, tetrahedron, etc., nested inside each other, like divine clockwork. It was a beautiful idea.
But he needed data to prove it, which led him to Tycho Brahe.
Yeah, the odd couple of astronomy. Tycho, the meticulous observer, maybe the best ever with the naked eye, gathering incredible amounts of precise data. Kepler, the brilliant theorist. They needed each other, but apparently didn't trust each other much.
And Tycho, on his deathbed, basically pleads with Kepler, right? Let me not seem to have lived in vain. He passes on this lifetime of observations.
And Kepler takes that data and tries to make it fit his beautiful, perfect, God-given model of nested solids and circular orbits, especially for Mars.
And this is the crucial moment. It doesn't quite fit, does it?
It's off by just a tiny amount, but a crucial amount. 8 minutes of arc. That's like less than a quarter of the width of the full moon in the sky.
So small. It would have been so easy to fudge it, blame the instruments, anything to save his beautiful theory he'd worked on for years.
But he didn't. This is the triumph of skepticism, of honesty. He trusted Tycho's data more than his own elegant theory. He famously wrote something like, "With these 8 minutes, we will yet chart a path to reforming the whole of astronomy." He chose the facts.
And those facts forced him to ditch the perfect circle, which everyone had assumed since the Greeks.
He had to. The data showed the orbits weren't circles, they were ellipses, slightly squashed circles. That was Kepler's first law. It shattered the old idea of perfect, unchanging ethereal heavens. It showed the planets moved according to physical laws, just like things on Earth. It was revolutionary. Skepticism won.
So if that whole sweep of history from the Ionians to Kepler feels long to us, the timescales involved in evolution are just something else entirely.
Oh, completely different league. Sagan uses that analogy. We are like butterflies who flutter for a day and think it is forever. Our lifespans are just blinks compared to the eons needed for evolution. It's one reason why Darwin and Wallace's ideas felt so counterintuitive, so hard to accept. We just can't easily grasp deep time.
And evolution runs on what? Death and time, basically.
Pretty much. Lots and lots of death organisms that aren't quite fit enough don't pass on their genes, and immense amounts of time for those tiny random changes, mutations to accumulate very, very slowly.
So where did it all begin? Life itself, we're talking maybe 4 billion years ago.
Roughly, yeah. Not in some pristine garden, but in the messy, organic soup of the early Earth. The atmosphere, the oceans were full of simple molecules zapped by lightning, bathed in UV light. And eventually, just by chance, a molecule formed that could make rough copies of itself, the ancestor of DNA.
Just a chemical accident, essentially.
A very fortunate chemical accident. And what's amazing is the universality of it. All life on Earth today, from bacteria to us, uses the exact same basic genetic code. 4 chemical letters, the nucleotides, A, T, C, and G.
And changes happen how? Just random types?
Basically, yeah. A mutation is just a change in one of those letters. Most mutations are harmful or neutral, but every now and then a tiny change offers a slight advantage. Better camouflage, maybe, better digestion. And that organism is slightly more likely to survive and reproduce. Slow grind.
It took a long time just to get beyond single cells, right?
Billions of years. Maybe 3 billion years ago, you start seeing cells clumping together, cooperating, forming the first multicellular life, like little communes. But the real game changer, the thing that accelerated everything.
Sex.
Sex? probably invented around 2 billion years ago. Before sex, evolution was painfully slow. You had to wait for individual mutations to accumulate one by one.
Like changing one letter at a time in a giant library.
Exactly. But sex allowed organisms to swap huge chunks of genetic information, mixing and matching whole paragraphs, pages, and books of their DNA. Suddenly, you could generate much more variation much faster for natural selection to work on. It kicked evolution into high gear.
And selection isn't always purely natural, is it? Culture can play a role. Like those crabs in Japan, the hike crabs.
Ah, the hike crab story. It's a fantastic example of artificial selection driven by, well, by folklore and history.
Tell us about it. It connects to a famous battle.
Right, the Battle of Dano-Ura in the 12th century. The hike samurai clan was wiped out, defeated, and many drowned themselves rather than surrender. The local legend grew that their ghosts haunted the seabed, reincarnated as crabs.
Okay. So
Right.
how does that affect the crabs?
Well, these particular crabs have patterns on their shells, and some of those patterns happen to look remarkably like a stylized, angry samurai face.
Seriously. Like a face.
Yeah, it's quite striking. So the local fishermen, who often revered the Heike story, if they caught a crab that looked like a samurai face, they felt it was disrespectful, maybe unlucky to eat it, so they'd throw it back into the sea.
So they were unintentionally selecting for the crabs with the clearest samurai face markings.
Precisely. Over centuries, by throwing back the ones that looked most like the legend, they increased the frequency of those genes in the crab population. It's artificial selection, driven entirely by a human story. It shows how culture and nature can interact in surprising ways.
That's fascinating. Okay, so moving from crabs back to us, the leap to consciousness. That required a massive increase in information storage, didn't it? Comparing DNA to the brain.
A huge leap. Our DNA, the genetic instructions in every cell, holds about 5 billion bits of information, which sounds like a lot, maybe 1,000 books worth. That's our inherited, ancient survival knowledge.
But the brain.
The human brain, with all its neural connections, estimates are around 100 trillion bits. That's 10 to the power of 14. Maybe 20 million volumes worth of information storage capacity.
Wow. So 10,000 times more information in the brain than in our genes.
And that difference, that massive extra capacity, that's where learning, culture, memory, foresight, everything we think of as uniquely human resides. It's what allows us to adapt within our lifetimes, not just over generations.
And the structure of the brain itself tells that evolutionary story, doesn't it? McLean's model of the 3 layers.
Yeah, the triune brain idea. It's a useful model. Deep down, you've got the brainstem, the really ancient part, handling basic bodily functions, breathing, heartbeat.
Then wrapped around that.
The R complex, the reptilian brain. This is where our primal drives live. Aggression, ritual, territoriality, social hierarchies. Think lizard brain. Very basic, very powerful.
And then the next layer.
The limbic system, which we share more with other mammals. This is the seat of strong emotions, parental care, social bonding. It adds complexity to the raw drives.
But the crowning achievement is the outer layer.
The cerebral cortex, that big, wrinkled surface, that's the powerhouse of conscious thought, intuition, planning language, critical analysis. Sagan calls it our liberation. It allows us to potentially override those older, more primitive drives from the R complex and limbic system to reason, to choose.
To choose something other than just reacting like a lizard or a baboon.
Hopefully. That's the ongoing human struggle, isn't it? Between the cortex and the older parts of the brain.
Okay, so we've journeyed from the vast cosmos down to the intricate wiring of the human brain. Let's zoom back out now to the biggest picture. The universe itself, its shape, its fate.
Right, cosmic topology. Modern cosmology, our understanding of the universe's origin and evolution, really rests on 2 main pieces of evidence for the Big Bang and expansion.
What are they?
First, the observation that almost all galaxies seem to be moving away from us. We see this through the redshift. Their light is stretched to longer, redder wavelengths, like the sound of a receding siren changing pitch. The Doppler effect for light.
The further away they are, the faster they seem to recede.
Generally, yes. And the second pillar is the cosmic microwave background radiation, this faint, incredibly uniform glow of microwaves coming from all directions in space. It's interpreted as the leftover heat, the afterglow, from the Big Bang itself.
pretty compelling evidence, but science always needs skepticism, right?
Yeah.
Are there any nagging problems, any data that doesn't quite fit?
Well, yes, there's the work of astronomers like Halton Arp. He spent years documenting cases that seem problematic for the standard model.
What kind of cases?
He found examples where you have objects, say a galaxy and a quasar, that look like they're physically connected, maybe a bridge of gas between them. So they should be at the same distance from us.
Okay. Thanks,
But
man.
when you measure their red shifts, they're wildly different. The quasar might have a huge redshift, implying it's billions of light years away, while the galaxy has a small one, implying it's much closer, yet they look connected.
So, how can that be? If redshift equals distance equals expansion speed.
Exactly. It throws a wrench in the works. Either some objects with huge redshifts are actually nearby, which contradicts the standard model, or maybe redshift isn't only caused by distance and expansion, maybe there's some other physical process causing some redshifts. Arp argued it meant, as Sagan puts it, something very strange is going on.
Which forces us to think about the fundamental nature of space, doesn't it?
Yeah.
Geometry, dimensions.
It really does. And this is where analogies become essential because we can't truly visualize higher dimensions. The classic one is flatland.
Right, the story of the two-dimensional world. Beings living on a flat plane, only knowing forward, back, left, right. No concept of up or down.
Imagine you, a 3D being, were to pass an apple, a sphere, through their 2D world. What would they see?
Well, first, nothing. Then a point appears, then it grows into a circle, maybe changes size a bit as the apple moves through, then shrinks back to a point and vanishes.
Right. To them, it would be bizarre. An object appearing from nowhere, changing shape mysteriously, disappearing into nowhere. They couldn't comprehend the third dimension the apple exists in. They're trapped by their dimensional limits.
So how does that apply to us in the universe?
Well, think about the surface of the Earth. For a 2D being living only on that surface, it feels infinite, right? You can walk forever and never hit an edge.
Yeah, it's finite in area, but it has no boundary. It's unbounded.
Exactly. Finite but unbounded. And where is the center of the Earth's surface? There isn't one on the surface. The center is in the third dimension, inside the sphere.
Okay, I see where this is going.
Now, just add one dimension to everything. Our universe, which we experience in 3 spatial dimensions, might be the 3D surface of a 4D hypersphere.
So our universe could be finite in volume, but have no edge, no boundary.
Precisely. And it could be expanding, like the surface of an inflating balloon. And this solves that puzzle. Where did the Big Bang happen? If the universe is like that hypersphere surface, the Big Bang happened everywhere on that surface simultaneously.
So there's no center in our 3D space.
Hmm.
Every point is moving away from every other point like dots on the balloon surface.
That's the idea. It explains why we see all distant galaxies receding from us, no matter which direction we look. We're not in a special central spot.
That concept of cycles, of vast timescales, actually echoes some ancient philosophies, doesn't it?
It really does. Sagan points out that Hindu cosmology is kind of unique among major religions in embracing truly immense timescales, cycles of creation and destruction that resonate surprisingly well with modern scientific estimates.
Like the day and night of Brahma. How long is that?
8.64 billion years. Longer than the current age of the Earth or the Sun. And that's just one cycle in an infinite series. They conceived of a universe undergoing endless deaths and rebirths.
And the imagery they used. Like Shiva's dance.
Nataraja, the dancing Shiva. Perfect metaphor. In one hand, the drums symbolizing creation. In the other, the flame of destruction. The universe constantly cycling through existence and non-existence. It's quite profound.
So what's the scientific view on our universe's ultimate fate? Does it expand forever or?
That depends on how much stuff is actually in it, how much mass, how much gravity. If there isn't enough matter to overcome the expansion...
But it just keeps expanding forever. It gets colder, darker.
Right. An open universe, fading out into heat death eventually. But if there is enough matter, maybe hidden matter, dark matter, black holes, stuff we can't easily see.
Then gravity eventually wins. Pulls everything back together.
The expansion slows, stops, and reverses. The universe collapses back in on itself in a fiery big crunch. A closed universe.
And if our universe is closed like that, gravitationally bound.
Then, in a very real sense, it fits the definition of a black hole. A region of space-time from which nothing, not even light, can escape beyond its boundary. So if you want to know what it's like inside a black hole, Sagan's answer is, just look around you. We might be living inside one.
Okay, that's a lot to take in. Let's bring it back closer to home again. Our solar system neighbors, they offer lessons too, right? Warnings, even. Starting with Venus.
Venus is the nightmare scenario, the ultimate cautionary tale about the greenhouse effect.
What's like there?
Horrific. The atmosphere is almost entirely carbon dioxide, about 96%. Thick clouds, not of water, but of concentrated sulfuric acid. And the surface, it's about 480 degrees Celsius, 900 Fahrenheit, hot enough to melt lead. And the pressure.
Crushing. 90 times Earth's atmospheric pressure at sea level. Like being a kilometer deep in the ocean. Probes don't last long.
So what happened? Why is it so different from Earth?
The scary part is Earth actually has a similar amount of CO2 overall. But most of ours is locked away safely in carbonate rocks like limestone and dissolved in the oceans.
But on Venus?
Being closer to the sun, it was always a bit warmer. That extra heat started to bake the CO2 out of the rocks, releasing it into the atmosphere. More CO2 meant a stronger greenhouse effect, which meant more heating, which baked out even more CO2.
A runaway feedback loop.
Exactly. An irreversible planetary catastrophe.
Yeah.
It shows just how unstable a planet's climate can potentially be. Our comfortable climate isn't guaranteed.
And we're currently pumping huge amounts of CO2 into our own atmosphere.
Yeah. From burning fossil fuels, we're playing with that planetary thermostat in a big way. And it's complex. We might be warming things up with CO2, but maybe also cooling things down in other ways, like changing the planet's reflectivity, the albedo, through deforestation or air pollution. We're messing with the system without fully understanding the consequences.
A dangerous game. Then there's Mars. A different kind of lesson, maybe. More about us, our hopes and biases.
Absolutely. Mars is a story of wishful thinking, largely thanks to Percival Lowell.
Lowell, wealthy Bostonian, built his own observatory, and he looked at Mars and saw canals.
Not just fuzzy lines. He drew these incredibly detailed maps of a vast, planet-wide network of straight canals. Built, he was convinced, by an intelligent Martian civilization to channel water from the poles to their dying cities.
It was a captivating idea. An older, wiser race struggling against climate change, but
wasn't real. Alfred Russel Wallace, the co-discoverer of evolution, pointed out pretty quickly that Lowell's own temperature figures showed Mars was way too cold for liquid water on that scale.
And later spacecraft, of course, showed zero evidence of canals. They were illusions. Probably, as Sagan suggests, the brain desperately trying to connect faint, blurry dots under difficult viewing conditions. Pattern recognition gone wrong.
Makes you wonder, as Sagan quipped, which side of the telescope the intelligence was really on.
But we did eventually send sophisticated probes specifically to look for life, the Viking landers in the 70s.
Amazing machines, like robotic grasshoppers with chemical labs inside. They scooped up Martian soil and ran experiments, right? Looking for signs of metabolism.
Yeah, 3 different experiments. They added nutrients, radioactive chicken soup, basically, to see if anything in the soil would consume it and release gas. Or they'd see if the soil could take gases from the simulated atmosphere.
And the results were?
Confusing, maddeningly ambiguous. 2 of the 3 experiments gave positive results. They showed chemical changes consistent with microbial life. And this happened at 2 different landing sites, thousands of kilometers apart.
That sounds pretty positive then.
You'd think so, but the problem was they couldn't definitively rule out non-biological explanations. Maybe some weird exotic Martian soil chemistry, some unusual minerals could mimic those reactions without any life being involved.
Like a false positive.
Possibly. And a crucial limitation. Viking could only scoop surface soil. It couldn't drill into rocks. And we now know from finding microbes inside rocks in extreme environments like Antarctica that rocks can provide shelter. So maybe Viking just didn't look in the right place. The jury's still out on Martian microbes.
That ambiguity, that complexity brings us back to the human condition, doesn't it? This paradox. We have this incredible cerebral cortex capable of understanding orbits and dimensions.
And yet we're still wrestling with these ancient, powerful, sometimes destructive drives from the R complex. Aggression, tribalism, ritual.
Before we tackle that head on, Sagan makes a point of addressing something else that distracts us, something that mixes cosmic awe with, well, nonsense. Astrology.
Ah, yes, astrology. Still vastly more popular than astronomy, sadly. People want that personal connection to the cosmos.
But does it hold up to scrutiny?
Yeah.
Any scrutiny at all?
Not remotely. The simplest test destroys it. Twins, born at the exact same time, same place, under the exact same supposed celestial influences, yet they often live vastly different lives, have completely different fates. If astrology worked, their lives should be near identical. They're not. Case closed.
So the planets don't control our personalities or destinies?
No. But we are connected to the cosmos, just Not like that. We're connected physically. The atoms in our bodies, the carbon, the oxygen, the iron, were forged inside stars billions of years ago. We are literally made of star stuff. That's a real profound connection, much grander than the small-scale, unimaginative fashion that the astrologers pretend.
Okay, so setting aside pseudoscience, let's face the real danger, the one born from our own intelligence. The technology that took us to the planets?
Is the same technology that enables nuclear war? Rocketry, guidance systems, it's the same fundamental engineering.
And the scale of the threat is just hard to comprehend. How many Hiroshima-level bombs does the world arsenal represent?
Sagan estimated it back then as equivalent to about 1 million Hiroshima bombs, all potentially deliverable within hours. It's suicidal madness.
He uses that chilling account from a Hiroshima survivor, a schoolgirl, to try and make the horror real, describing the darkness, the injured people who did not appear to be human.
It's vital to remember the reality. It's not abstract numbers. It's unimaginable suffering. And beyond the immediate blast, fire, radiation, the long-term effects of a major nuclear exchange would be catastrophic.
Like what?
Destruction of the ozone layer, leading to lethal levels of UV radiation, global cooling from dust and smoke, blocking the sun, a nuclear winter, ecosystem collapse, maybe insect plagues, widespread immune system failure, long-term genetic damage, mutations. It's planetary suicide.
And Sagan links this tendency towards mass violence back to those deeper brain structures.
Yeah, quoting researchers like Richardson who showed war is on a continuum with individual murder. Murder, writ large, driven by those R-complex urges, territory, tribalism, ritualized conflict. Einstein called war an illness of childhood.
So the challenges for our cerebral cortex, our reason, our foresight, that 20 million volume library to finally get control over the lizard brain, to manage those ancient impulses before they destroy us.
It's the essential task of our time. We have to grow up technologically and emotionally.
If we manage that, if we navigate this perilous phase, the stars really are within reach, aren't they? We have ideas, designs.
We do. Things like Project Orion, using controlled nuclear pulses for propulsion, or Project Daedalus, designing a fusion-powered starship. These aren't science fiction, they're engineering studies.
How fast could they go?
Maybe 10% of the speed of light, which sounds slow compared to light, but it's incredibly fast. A trip to Alpha Centauri, the nearest star system, at that speed would take about 43 years.
Manageable. Less than a human lifetime. Or maybe longer trips with multi-generational ships, or hibernation.
The possibilities are there. The technology is conceivable. The biggest obstacle isn't physics. It's us. It's whether we can survive ourselves long enough to make the journey.
That's the stark choice, isn't it? The rockets are on the launch pads. Will they carry probes to explore, or warheads to destroy?
Who speaks for Earth? That's the question Sagan leaves us with. We have to transcend our narrow nationalisms, our tribal loyalties. We have to see ourselves as citizens of a planet, a single species with a shared destiny.
Our responsibility isn't just to ourselves, but to the cosmos that produced us. If we don't self-destruct, this time right now, this challenging, dangerous moment, could be the very beginning of our journey out there.
It's been quite the trip, hasn't it? From the Big Bang through stellar evolution, the origin of life, the rise of consciousness, the vastness of space and time, all the way down to the atoms that make us up.
And the core message seems to be
That we are the local embodiment of a cosmos grown to self-awareness. We are the universe experiencing itself, star stuff, contemplating the stars. It's an incredible realization.
and it makes every single human life seem incredibly valuable, doesn't it? In all those billions of galaxies, there's nothing else quite like a human being. We are precious.
Absolutely. And that journey through cosmic structure, through topology and dimensions, it leaves us with some mind-bending possibilities, doesn't it?
Right, that final thought experiment. Building on flatland, and the idea of our universe is maybe a 4D hypersphere. What if that pattern continues infinitely?
What if you could zoom in infinitely? What if an elementary particle, like an electron, isn't just a point, but contains within it an entire closed miniature universe?
Whoa, okay. Then the other way, zooming out.
What if our entire observable universe, galaxies, everything, is just one single elementary particle within a vastly larger, higher dimensional metaverse, an infinite hierarchy, up and down?
So, what kinds of physics, what kinds of reality might exist in those higher dimensions or within those sub-universes inside particles, things we can't even begin to imagine?
Exactly. Laws, technologies, forms of existence completely beyond our current comprehension. The sheer scale of cosmic possibility hinted at by topology might be truly infinite. And Well, that's definitely something to ponder until our next deep dive.